Let's now consider what the physical dimensions are of viscosity and how it relates to fluid properties. We start with the Navier-Stokes equations with constant dynamic viscosity, mu, which takes this form where we have our momentum equation, our fully nonlinear momentum equation, with a right-hand side term that's a viscosity term, a Newtonian viscosity. So what are the dimensions of this equation? Well, and what are the dimensions in particular of our coefficient of dynamic viscosity, mu? How is it related to length and time? Well, a strong principle in terms of understanding equations is that every term in a partial differential equation like this, when the equation's in dimensional form, every term has to have the same dimensions. So if you want to know the dimensions of an unknown term, like this term over here, our viscosity operating on a Laplacian of flow, we can compare it to a term where it's easy for us to figure out the dimensions, like a time derivative of our flow. So the way that we'll find our dimensions of mu are to start by comparing these terms. So let's consider the dimensions of these. And we'll write the dimensions in green, just so they stick out. Well, the dimensions of our first term here, of our d by dt of u, well, this has dimensions of u. The dimensions of u, this is like meters per second or centimeters per second. So this is a length per time. And it's got a time derivative, a 1 over a d by dt. And that's really like a 1 over time on our system. So the dimensions of this thing, the dimensions of u, these are length squared, or excuse me, length per time squared is the form that partial with respect to t on u takes. Okay, so let's collect our other system here. So we have we're comparing this to mu over rho, operating on the Laplacian of u. So what's the dimensions of this term? Well, our velocity, this has dimensions of length per time. And our density, this is like a mass per length cubed. Okay. What about this? What about our gradient here? Well, a Laplacian, right? This is a d by dx squared in a real sense. So this has units of 1 over length squared. So the combined units of this system, they are whatever mu's units are, mu over rho, whatever that is, times collecting our other units for our Laplacian, length to the minus 2, and our velocity, that's a 1 over length times time. So let's now equate these two, right? So we have our d by dt of u. This has to have the same units as our mu over rho grad squared u. And I'm gonna write this in kind of a funny way. I'm gonna collect the terms out here. So I'm gonna write here's our length per time squared. Those are all the dimensions of the u vector and the t. So I'm going to do something kind of cute for a moment. I'm going to actually signify that the u and the t no longer have dimensions. Right? I've gathered all their dimensions. So let's write them in purple. Purple is a great color. This is the dimensionless. This is the dimensionless u and t right here. And the length and time we've pulled out here, these are the dimensionful. This is all the physical units of this part of the equation. Okay, let's do the same over on the left-hand side. I'm going to leave the mu and the rho alone. I'm just going to pull out the 1 over length time that comes from our Laplacian operating on the velocity. So once again, I've pulled out all the dimensionalness of those. I'm going to write the dimensionless form in purple. So let's write that as del squared u on vector. Okay. So here we are. We've got our dimensions in green pulled out in front of each of our terms. We've got our dimensionless bits, and we've got our unknown dimensional quantity here. So let's start by looking at our unknown dimensional quantity. What are the dimensions of this unknown dimensional quantity? Well, this unknown dimensional quantity, mu over rho, this has dimensions just by taking the bits in front of it and equating to the bits on the other side. This has an LT times an L over t squared. So we come through and we cross out the t in one of the powers, and this has the units of length squared per time. Okay. And we call this, this comes up often enough that we actually call this a special thing. We call this the kinematic viscosity. The kinematic viscosity nu, the Greek letter nu, and it's related to the dynamic viscosity mu. The kinematic viscosity has units of length squared per time, and the dynamic viscosity has some other units. So let's look at these two in turn. So we have our kinematic viscosity. This has units of length squared per time. And this is a diffusion-like coefficient, and this is given a special name. It's called the Stoke. You'll see things listed as having stokes of viscosity. Our other viscosity, our dynamic viscosity, mu, this is equal to rho times nu. So this has some kind of different units. It's got a unit of a mass, right, for our rho over length cubed for our rho times the length squared over our time. So this, when these lengths cancel there and there, this turns into a funny unit of masses per length time, and we call this Poisse. And we're going to come across Poisset, who the Poisse is named after. And this weird set of units, this is why you'll see viscosities for fluids like water often quoted as like grams per centimeter per second. And you'll look at this and you'll be like, wait a second, but I want something I can make quick dimensional analyses from, something like a centimeter squared per second. How do I link the two together? Well, the two are linked together by knowing the density of the system you're looking at. And luckily for water, of course, the density, it tends to be very, very near 1 gram per cubic centimeter. And so for water, a mu and a nu are roughly equal to each other in terms of numeric magnitude for water under sort of typical conditions. For water, this is equal to 1 centipoise and 1 centistoke, and these are values of roughly 1 or 10 to the minus 2 centimeters squared per second, or 10 to the minus 2 grams per centimeter per second.